Hi, this is Professor Stugard, and in this video, we're going to be making a linear regression model in Python. So the first thing we need to do is, of course, upload our data set that we're going to be using. And so I've already downloaded the Boston housing data set, so let's make sure we upload that into our Jupyter. All right, and now we will create a new Python file for our project. So let's not forget to title this. So we'll call this our linear regression model, and I'll put my name on it as well. All right, so the first thing we want to do though is we want to actually take the time to make sure that this project looks professional, kind of like we would expect a report done if we were working in this type of field. So one of the things we can do first, if you look at, again, the way this Jupyter is set up, we see that we have the word code here. And so that means that this cell is designated as a cell that we type our Python code. But if we click down, we can see we can also do it as a markdown, or we could do it as a heading. But we can use markdown to create our headings as well. So if I do this as a markdown, now we can use the rules from Markdown to actually add text into our files for someone to kind of read and to help interpret what we're doing, besides just commenting our code. So to create headings, we do the pound sign. And so you can kind of see if I do one, it's pretty big. You actually see it gets smaller as we do more, and then eventually we're just back to regular text. So maybe we'll do 2 for the top. And so what we're going to be doing here is we are using the Boston housing data set to create our linear regression model. So again, if I'm going to title this, let's call this the Boston housing linear regression model. And if I run this now with the shift enter, we see, oh, that kind of gives me a tab there. We can also add just regular text. So again, if I change my next one, again, the default's going to be code, but if I change it back to markdown, now I can just take my text and I should type something like, this is prepared by Nick Stugard. And I run that, and that gives me some text as well. And again, I can add another markdown, and I can add kind of a description of what we're going to be doing. We will be using a data set about Boston housing to create a linear model used to predict the price of housing. And again, we could add a lot more if we wanted to, but for now, I think that's probably fine. So obviously with all of our projects, now that we actually are going to get into some of our code, we do want to comment, and the first thing we want to do is really import our libraries and then our data set. But we'll import our libraries first separately. And so as usual, we're going to import pandas as PD. That's obviously our one that lets us kind of use data frames, and then also import numpy as MP. And again, that lets us do kind of math in Python, at least the math that we need for what we're going to be doing. And again, those are pretty much the 2 defaults that we always load every time we're ever doing any project in Python. It's just kind of the default. I also know that I'm going to want to make some graphs as well, and there's different packages for graphing, but we're going to import the matplotlib.pyplot. We'll do that as PLT, and that again will be kind of our graphing, our default graphing software. Although we'll probably import some other packages later on. Again, this is kind of a good place to start. So we'll run that code. That all good. That ran without any issue. So the next thing we'll do is import our data set. And so we're going to call this our Boston_df for Boston data frame. And again, we downloaded that CSV file, so now we just need to kind of call it so that we can make it this object Boston_df. And so we're going to do that with the read CSV file. That, of course, comes from the pandas library, so we do have to put the pd dot and then our read underscore CSV, and then our argument. So we got to put our parentheses and then our quotes, and it is going to be the Boston housing data set. Again, we got to remember that if we're using functions from specific packages, we put that, however we imported it, what that kind of our abbreviation is, we want to make sure we put that first. Now in Python, in Anaconda at least, in our Jupyter notebooks, we could either type it exactly as it's written, or if we hit that tab button, it'll bring up everything that is in my my home page for Python. So I didn't have to scroll too far. It's in alphabetical order. We have Boston housing. So I'm going to import that. And then I want to see what this looks like. I want to see what this data looks like. So we'll take our Boston underscore DF, and we're going to apply functions to it. And so the syntax in Python, again, I'm going to take my object, in this case the Boston data frame, and I want to apply the function head. So I can just see the first couple of rows. If I run my code, here we go. So we see that, again, if I look at just the head, my columns, I have Crim, Zin, Indus, Chaz, Nas. Okay, we had a bunch of things here. I included, this is the description of each of these variables for the Boston housing data set. So we have 506 instances, 13 attributes or 13 variables. So CRIM, that's our crime rate per capita by town. ZN is the proportion of the residential land zoned for lots over 25,000 square feet. Indus would be the proportion of non-retail business acres per town. The CHS one represents our Charles River. So that is a categorical variable where it's a 1 if it is on the river, on Charles River, or a 0 otherwise. So kind of the Boolean there. NOx is the nitric oxides concentration. And so, again, this data set became kind of famous because of an analysis done back in 1976. So also this data set is from 1970 census. But in the paper, they were looking at, are people choosing houses, and does house price depend upon the air quality? And this is what they were using for air quality, was the nitric oxides concentration in each of these neighborhoods. RM stands for the average number of rooms per dwelling. Age is the proportion of owner-occupied units built prior to 1940. So again, remember, this is a data set from 1970. Most of this data is pulled from the 1970 census. So again, it's a little bit older. DIS would be the weighted distances to the 5 Boston employment centers. RAD is the index of accessibility to the radial highway system. Tax would be, well, the tax rate per $10,000. The PT ratio is the pupil to teacher ratio by town. And then we have this variable B. So B, here's the mathematical formula where BK is the proportion of blacks by town. So this used to be the default data set for sklearn. In fact, this is pretty much the default data set that almost everybody learned linear regression on. sklearn has since removed it as a default data set because it is possible that that is someone could consider that to be a racist variable because it's the proportion of blacks by town, not Black Americans or African Americans. Yeah, I don't know. And then LSTAT, that is the percentage of lower status of the population. And then the MEDV, the median value of the owner-occupied homes. So we can see here the number of attributes. The median value is typically the target. And again, that's going to be the target for us as well. Here we can see all of our variables here. Our target variable is going to be the median value, this last one. And so the other ones are going to be our features. And so we're going to do a couple of things. We'll explore this data set and then hopefully figure out what our best predictor variables are. So we imported our libraries. Now let's create another markdown, and we're going to use like 4 pound signs to make this heading. This is going to be where we do our exploratory data analysis. This is where we really start to dig into this data. That looks and see what we have. So we can, of course, do, so boston.df. Yeah, we're typically going to start there because that's our object. And in Python, we take our object and then we apply our function into it. So it's kind of like the pipe from R. If we remember that, we start with our data and we pipe it into our function. In Python, it's very similar, except we just use that period. So the first thing let's do is let's take a look at our info function. And we'll take a look here. All right, so we see that there's 506 entries. So again, that's 506 observations. We have all of our variables, which we already kind of looked at. We take a look. Looks like they're almost all there. We can see, oh, actually, I already see that looks like the RM for the rooms, that's probably going to be an issue because we're missing at least a little bit of data. Let's see if there's any other data missing. Of course, we would do that with our isNA. Now, we also want to make sure we look at this. So, well, all right, let's just do this. So boston.df or boston_df dot, and then we'll run our isNA function. And so we see, oh, it's just running back a bunch of falses. Okay, so that's not super useful for us. So what we can do is remember that these true falses are Boolean values that are also stored as ones and zeros. Ones for true, zeros for false. So I can add another function at the end of here. So we're going to take the Boston data frame, we pipe it into the isNA function, then we're going to pipe it into the sum function. And that should add up how many trues there are for us. And so we run that, and we see that, yeah, so the RM, we have 5 observations that are missing the number of rooms. And that's the only missing data here. So what we're going to do now is we are going to, I think we're just going to drop those rows. We're going to remove those rows. It's only 5 of them, so we're looking at, less than 1% of our data. I think we'll be fine just removing those from our data set. So again, we're going to remove the missing data observations, which again would be those 5 rooms. So I'm commenting my code here. And so we want to remember that I'm going to remove it, but I need to also restore it. I got to overwrite the Boston data frame in my environment here as well. So you could call it Boston_df cleaned or something else, but I think we can just overwrite it because again, we're only losing like 5 data values. So we're going to do that by taking our Boston.dataFrame and then just the drop NA function. We'll run that code. It should overwrite the Boston data frame. And again, what's nice is that I can kind of go back and I can actually take a look. I can rerun this code because again, now Boston data frame is something different. If I run it, yeah, now I'm down to 501 entries and they're all non-null. We'll double check with the isNA. They're all zeros. So we dropped our data and that is pretty good. So we did our exploratory data analysis. We dropped our missing data. Now what I want to do is I want to figure out what are my best predictor models, or what am I best predicting variables. So the way we're going to do this, again, we're doing a linear regression model, which means we want to find our linear correlation coefficient, and whichever one has the highest absolute value, that'll be the ones that we choose for this particular analysis. So again, I'm going to comment my code. I want to find my correlation coefficients. And what's nice is that, again, this is just the correlation function, but if I run so if I take my Boston underscore data frame and I run my function correlation, which again is the CORR, and then again, that's my function. If I run that code, it gives me my correlation coefficients all as this big table. That is really, really hard for me to interpret. I don't know what's going to be the best ones to use. So I'm going to do 2 things here. I am going to store this table of data as its own object called the core. So CORR, so maybe core underscore for Boston. And I'll run my code. Now it disappears because again, we're storing it. We're not having we're not having it actually outputted. We're not looking at it. We're telling the code, okay, We don't need to display it. We want to store it. And now to store it, I want to see it as a heat map. So let's comment my next cell. I want to go ahead and make a heat map for my correlation coefficient. I think I spelled that wrong. No E there. Okay. Now to do this, to make a heat map, we do need another package. And so we're going to import the Seaborn package. So Seaborn is another package that lets us make visualizations. It's got some really cool tools in there that go kind of beyond the typical matplot ones. And so we're definitely going to import that. The default that we import that as, our abbreviation is typically SNS. And then I want to basically call my heat map function. So I'm going to do my SNS.heatmap. That's my function. And inside, so I want my data to be my correlation Boston. Remember, we can always use our functions this way and denote all of our arguments inside those parentheses. And so since I'm going to be doing a couple different things here, so again, the heat map is going to create a color-coded picture of the numerical data that we've already kind of put in. And so I want to first do my Vmin and Vmax. That'll tell me what are the maximum numbers that I'm looking at. What should my heat map go from? And so my minimum number should be -1. If you remember, the correlation coefficient goes between -1 and +1. -1 being a perfect negative association, +1 being a perfect positive association. So Vmin would be -1, Vmax would equal +1. I want to center it also at 0. So again, that just basically gives me my scale for how I'm going to color my heat map in. Then what else can I do? Well, let's do, annotate. I'm going to set that to true because I want to see my values on my heat map as well. I don't want just the colors. I actually want the values as well. And then I'm going to lastly do my CMap. This is where I choose the colors to use. And my favorite, and I think this is the default anyway, is the VLAG where it goes between blue and red. So let's see what we got here. Let's see if this works. Okay, so we have our heat map. It is color coded. It's got all the numbers on there. This is kind of hard to see. It is definitely all written on top of each other. It's definitely way too close. So I'm going to have to do two different things. So first of all, again, if you remember, we did this one. We had that big table of our correlation coefficients. There were all these large numbers. Let's round that, in fact. So I'm going to go back now to where I found my correlation coefficients and stored them. And I'm going to use the round function, and I'm going to round them to 2 decimal places. So that'll round it. And then over here where I'm making my heat map. So what I want to do now is before I make my heat map, I need to designate how big I want my picture. So again, that looks really small and really cramped onto my screen. I want to make it a bit bigger. And so that is going to be PLT. So now, again, we're kind of combining the matplot library along with my Seaborn library functions. So PLT.figure. So again, this is going to basically, I can set a bunch of different arguments here for what my figure is going to actually look like. And really what I want to do is my fig size equals, and then another set of parentheses, because again, it's going to set how wide it is and how tall it is. Those are going to be my 2 variables. So we'll try 10 by 10. We'll see if that looks good. And then also my last line, I'm also going to do the plt.show so that hopefully I get rid of some of this notation. So let's see how this looks now. I like that much, much better. So again, you can play around with the different figure sizes, make it whatever size you want. Again, I annotated it so I can see my values up to the 2 decimal places. And you know what? Let's make this full screen so that we can see everything together. And again, this gives me a really good visualization. So what I want to find is what are the best two variables for my median value. That's what I want to predict. So which variables are going to have the best correlation coefficient to make those predictions? And as I kind of scroll through here, I see 0.7. That's pretty good, kind of a dark red. And then negative 0.74, kind of a dark blue. So those are both going to be pretty good. Those are they look like they're the highest ones. So that's what we're going to use to make our predictions. But again, we can actually find these numerically as well. So I can do, so like I said, the correlation coefficient goes between -1 and +1. So we have negative or positive values, which sometimes makes it a little difficult to kind of determine what's going to be best. So we use the absolute value function. So that's the ABS, and that'll tell us the absolute value. So it'll make everything positive so we can compare positives and negatives. And then I can do my correlation function, and I can actually apply my correlation function to a very specific variable here. So in this case, the variable MEDV, and I want only the ones that are going to be bigger than 0.5. That's right. It's core underscore Boston. There we go. That's how I had it saved. So I can go through and I see, okay, the absolute value of the correlation Boston one with, again, being applied to my median value, its RM is true. The pupil to teacher ratio is also true. And again, we can see over here that that is 0.51. The LSTAT is true. And of course, median value, it's going to have a perfect correlation to itself. So that's pretty straightforward. So we see the ones that work. We can also do this another way as well. I can print, and we can do... Okay, let's go back and do the Boston underscore DF data frame. We're going to apply the correlation function to it. From the correlation function, then we're going to apply the absolute value function to it. So again, we're kind of going back a little bit. So we take our Boston correlation coefficient, our Boston data frame, we run the correlation coefficient function to the entire thing. We find the absolute values of those. From there, I want to take the n largest, so that's another function. So again, basically it's going to look at that whole table of values. It's going to pick the largest ones. I'm going to tell it to pick the 3 largest ones. So I actually want 2 predictor variables, and again, we know that what the best 2 are. This is just another way we can use the code, because again, there's lots of ways we can do this, and you can pick which one you kind of like the best. The 3 largest, and again, it has to be the ones compared with, and we need our quotes, the median value, and those n largest, and we want to index it. We want to see it as kind of an index here. So let's see. So perfect. We see that the best predictor is obviously itself, because it's going to have a 1-to-1 correspondence to itself, and then the next best would be LSTAT, and then RM, the rooms, would be the next one. So again, we'll just real quick, let's go back and look. So LSTAT, that is the percentage of lower status of the population. So again, we're talking socioeconomic status, and then RM is rooms. So it looks like those are going to be our best 2 predictor variables. So now that we figured that out, let's go ahead and actually write that into our markdown file. So the top predictive variables to predict the median house value. Maybe I'll use the actual name. The top predictive variables to predict and MEDV are LSTAT and RM, which are the percentage of lower status and number of rooms respectively. Hopefully I spelled that right. All right, we run the code. So the top predictive variables, MEDV, and the top predictive variables to predict MEDV are LSTAT and RM. Now, if you look, though, that's in the same font as just my regular text, but these are variables, and a lot of times we do that in kind of that Courier new font. If you want to actually denote these as those variables, as basically text chunks of your code, we can always edit this. So I double-click my cell, and if we add the tick marks, so that's the one that's right next to the number 1 on your keyboard. It's the tick marks. It's not an apostrophe. If I put those in the tick marks, and again, we see kind of the color change there. If I put those in the tick marks and then run my code, now it puts those in kind of my code font, the font that my code's going to be in, which I think is kind of nice and just adds an extra layer of kind of professionalism to this type of report. So we know what our best two are. Let's make sure they actually do what they're supposed to do. So we should definitely visualize the data now. So I'm going to now visualize these variables as a scatter plot. And that will hopefully show me that there should be some sort of positive association and negative association with these two variables. Hopefully it'll look good. So we'll do plt.scatter. So that is our function for our scatter plot. The data, we're going from our Boston data frame. And actually, so yeah, let me actually define these. So in my scatter plot, I got to define my x variable. By default, x is first, y is second, so I could have gotten away with this. But my x variable is going to be the Boston data frame. And again, I want my predictor variable or my explanatory along my x. So we'll start with the LSTAT. We'll start with the LSTAT. That'll be my x variable. So again, we're taking the Boston data frame, the column for LSTAT, that'll be my x coordinate. And then my y will be from my Boston underscore data frame of the median value, MEDV. Okay, so we'll see. We might update this a little bit as well. I always want my labels as well. So my x label for my x-axis, again, I'm going to call this the LSTAT. If you want, we could actually, use the description, the percentage of lower status. But for now, I think I'm just going to stick with what my variable names are. That's something we can always go back and change this later. That's the beauty of doing things in this code. And then lastly, PLT show, because I want to see my graph. Let's see. The scatter LSTAT is not defined. How is LSTAT? Oh, obviously it's not. I'm sorry. When we do our x and our y coordinates, since these are the names of the columns, I have to put the names of the columns in our quotes. Whoops. Forgot about that. We all make mistakes. All right, so here we go. That looks like it is a general negative association pattern. It definitely seems like we are going, down, in a negative association. Definitely looks like a pattern there, so I think that will definitely work. Now let's do it for rooms. I'm going to be lazy. I'm going to copy and paste. Actually, no, I'm going to be efficient. Why would I say lazy? I'm going to be efficient, where I'm going to change my x coordinate now to the RM variable. It means I also got to change my label to the RM variable. And again, with the scatter plot, we can do other things as well. So like I said, we can change color, we can change size, we can change maybe the marker to equal the O. Let's see what that's going to look like. Oh, that is the default maybe. Oh no, it looks a little bit brighter. The marker's the O. Again, like I said, we can change other things too. We can change the color equal to red if we want to. You know, make it red. And again, it looks like we have a general pattern here. There's definitely a positive association. It does seem like there's some weird grouping here. I have a feeling that this data set might not be perfect. And everything it looks like is, because it seems like we have this weird cap at 50, which is also true there, although they're much closer together there. But either way, we definitely have a general pattern here. I think this is going to work. Now, what's really cool is that, so again, we just did 2D scatter plots. We can make a 3D scatter plot as well. So this is a little bit more complicated. We're going to have to import another package. So and this one is going to be called mpl_toolkits.mplot3d. So again, this is another package that does 3D graphing, I guess, for us. And we're going to import this as capital Axis 3D. So we're going to import another toolkit. So now, again, this time we're going to, this is all to make a 3D scatter plot. So we're going to have to define a few things. This is a little bit more complicated, so, you know, follow along best you can. But we have to create a couple objects here that go a little bit beyond what we would typically have to do for just a 2D scatter plot. So the first thing we're going to have to do is we're going to create an object called fig, and that's going to be plt.figure. And again, we want to set our fig size just like we did earlier. We want it to be pretty big, so, you know, we'll start with, what did I do here? 1010. We'll see what that looks like if I do another one that's 10 by 10. We might want to make it bigger or smaller, you know, all depends on what we're doing. So again, I'm creating an object, and that object, I just know the size. All I've done is define the size. Now I got to create another object called AX, which is going to stand for our axes. And so that means we take our object that we just created, figure, and I'm going to run the function subplot. And subplot is a great function that lets you basically graph functions on top, graph plots on top of plots, or graph a bunch of plots in a row. It's a very useful tool when it comes to data visualization. And I'm just going to set it to 111, and then the projection is going to be in 3D. So again, I want a three-dimensional plot, and so again, it basically means we're going to combine two different scatter plots together. Okay, so we've created two objects. Now we need to actually do something with those two objects. So we're going to make our scatter plot now. So the AX, we're going to apply the scatter plot function, which is just scatter. And we're going to basically just pull what we did before. So my first variable will be from my Boston underscore data frame, and it will be the lstat, comma, and then my next variable will be from my Boston underscore data frame, and that will be the rooms. Again, don't forget those quotes, right? So again, those will be my two dependent variables, sort of. And then the last one will be the Boston underscore df mdv. So again, that's going to, oops, almost forgot my quotes. So that's basically going to be my z-axis. That'll be kind of my height. And again, if we can do something fun with the color, maybe we'll set the color, I don't know, we did red before, we've done blue. Let's see if green looks good. Who knows? Before I run this, as always, I want to do my labels. Again, we're using this 3D one, so on my object at AX, I'm going to apply the set underscore X label, and that's going to be lstat. I want to ax.set my underscore y label. And that will be the rooms. Yep, RM. So like I said, we did the scatter plot. I could have set those as X, Y, and Z, but by default, it's going to know that they come in order. AX.set. And the last one, underscore my Z label. And that will be my median value. And lastly, let's just do our plt.show function. Let's see what we get. All right, so here is our scatter plot in 3 dimensions. Now there's other packages where we could actually grab and rotate. We could actually also update some of our arguments up here and rotate it slightly differently. But again, it looks like when we compare these together, we do seem to have a pattern. Like there seems to be a grouping to these dots. It definitely seems like there is a pattern that we can try to describe with one of our machine learning models, in this case, linear regression. So yeah, let's actually start making our model. All right, so I'm going to create a new markdown because this is going to be a new header. I think I did 2 before. So now we're going to go ahead and we're going to basically train the model that I want to use. We're going to train and create our model. And so let's first define what we want our features to be. So again, right now I'm still working with the Boston the Boston data frame. I don't need all of those variables. So let's just pull the variables we want. We're going to use capital X. Here, I'll comment this cell. We're going to basically define the features. And so we use capital X. That is typically our default variable for what we want our features to be. And so I'm going to put my features into a data frame. I want to basically pull those 2 columns that I'm going to use, the LSTAT and the room. I want to pull those 2 columns and I want to store them as their own separate data frame. And so again, that's what I'm doing right here. I'm creating a separate data frame called capital X that is just those 2 variables. So we had to do the pd.dataframe function. Again, that's saying we're going to create a new object called X. If I want that object to be a data frame, I have to use this data frame function. And so then I'm going to pull the specific columns. So probably the easiest way, we'll use, again, a NumPy function, which is just our C function, which stands for column, or again, right, we use the C function for vectors. We do want to do an underscore here. That is just the kind of the syntax for this. And I'm going to pull from my Boston data frame this one last time, the LSTAT column. And then I'm also going to pull from the Boston underscore data frame. And then again, square brackets so that we get the column, then the quotes, name of the column to be rooms. So, okay, so we have the C, that's closed, good. Okay, so again, what's nice about Python, again, if you kind of go to the end of each thing that closes, it shows you in green. Now my C function to create my columns, that part has closed. If I click to the outside here, we're still in my data frame function. So inside my data frame function, I still have another argument. I need to define my columns. And so my columns, I just want to name them. So the columns will equal, and again, it'll be LSTAT inside, that column, and then comma RM inside that column. And that should work. Of course, I created that and I have no idea what it looks like because, again, it created it and it stored it. I want to actually look at it. So inside here, I'm going to put one more. I want to actually go ahead and print capital X. I don't want the whole thing. I'm just going to print just the head. And let's see what that looks like. Good. That looks like that worked. So now I created, again, what I did is I created a separate data frame called capital X that is just taking those 2 columns from my Boston data frame LSTAT and RM. The second part of it is I name those columns what they originally were named, because otherwise they wouldn't have a name. And I still want to be able to look at that. And so it looks like that was all good. So those are our features. Now we want to define the target. And it'll be pretty much the same idea, except for defining the target is typically a lowercase y. So again, we're doing linear regression, so hopefully this kind of makes sense. It's like that y equals mx plus b. I want to predict y by plugging in values for x, and so I'm going to be plugging in for my features to hopefully predict my price. Now in this case, I don't necessarily need to make this a data frame. It's just going to be that one column here that I'm going to check against. So, and I know that y is going to be the median price value. There's really no need to name it. I know exactly what I'm doing. And so I can really just pull that one column and that should be fine. We can always double check. Like I said, we use the print function, y dot, and then the head function. Yeah, and there we go. It's there. And so again, we define the target. It is the median value. And we defined the features, LStat, and rooms. All right, so we did all of that. Now we've just pulled basically those three columns from my original data frame. And we have them now stored, one separate for our features, one separate for our targets. So because this is machine learning, we have to create our training and test data. So from sklearn, again, sklearn is basically kind of like the default, most commonly used machine learning library and kind of database for Python. So we're going to be pulling from there. It's huge. So I'm actually going to be very specific about what I want to pull. I don't want to pull the entire sklearn library. That would take forever. So I'm just going to pull very specifically the model selection, because I want to be able to select which model I want to use. And from there, I want to import my train and test split function. So again, that will take my data set and it will split it into my testing and my training data set. Let's see. I could probably set a random seed here, but I think I can actually do this in the next part as well. So we're going to be using the test train split function, right? I'm pulling that specific function from my sklearn model. Like that's the one that I'm pulling. And so what's really nice about that is it will create my test and training data all in the same function and will create that split. So we're basically, again, we took our original data frame, we separated into one for our features, one for our target, and now I'm going to have to take each of those and split them one more time into the testing and then the training data, right? With the training data being bigger than the testing data, obviously, so we can train, and then we'll just test to see how well our model works based on that testing data that we've kind of set aside. We can all do this in the one function. And again, the idea is we're not going to have 4 different sets of data really. So again, this function lets us all do this in one line of code. So the first will be my x train data and then my x underscore test data. So again, we're going to create those two. We also want to create our y underscore train data and our y underscore test data. We're separating each of those with columns. Again, try to remember to do capital X's and lowercase y's. We're creating 4 different objects now, and we can do this, like I said, in this one line of code using the train underscore test underscore split function. Inside this function, again, I can denote a few different things. First, I got to denote what's what, and capital X and lowercase y, right? That's the first 2 for X. Train and X test come from X, and the Y train and the Y test come from Y. We could do different ones if we wanted to. Some of the other ones, the other arguments, we could do test size. How big do I want my testing data to be? And so we'll do the 25-75 split. That's pretty much default. It's either 80-20 or 75-25. We'll do the 75-25 this time. And then the last one, we will pick our random underscore state to be equal to, and this is basically setting our random seed so that hopefully our data will match at the end. I'll pick 5. And we'll run our code. Hopefully this worked. Let's print our X train shape. Let's just see what the shape of that data is. 375 and 2. So good. That means our original, what do we have? 501 variables, I think. It pulled 375 of them for our training data, which, and if we do 501 times 0.75, oh yeah, we get 375. So good. It did what we wanted it to do. We can double check here. I'll add another one. We can print our Y train.shape as well. We'll take a look at that, and that'll be, yeah, again, just 375. So our sizes match here. That's good. We could also, check X underscore test and run our shape function and print our Y underscore test shape as well, just to check that they have the same shape. And good, yeah, then the 126. So again, that kind of makes sense. Those two numbers are going to add up to the 501. Again, one has, they both have the same size, 2 variables. All right, good. So everything looks like that was done. Well, we set up our testing and our training data. So the next step is we need to actually go ahead and create our model. And so again, we're pulling from sklearn. We don't want to pull from the whole thing. From sklearn, I just want to pull my linear model. All I want to do is create a linear model. So from sklearn.linear model, again, which is a kind of a subset of that whole package, we're just going to import the linear regression function. Capital L, capital R, linear regression, all one word. Yeah, I think in the same code, and maybe I'll even put a space there so we can see the import separate up there. But so from this, I got to create my model. So my model is going to be an object. I'll just name it model. Maybe we should be more specific. This will be my housing model. And so my housing model comes from my linear regression function that I just pulled. I'm not going to fit anything in there just yet because my linear, so again, kind of the syntax here, what we have to do with Python, I'm going to create this object called housing model, and the housing model is going to be my linear regression function. And now that I have my housing model as an object, now I know that that object is going to be a linear regression model. That's kind of why I pulled it. And I want to fit it. My function now is I'm going to apply fit, and I'm going to fit it to my X train and Y train data. So I'm going to create a linear regression model using my training data. I'm going to set that to fit, and my output is linear regression. I think that means that it created a model for me. So now I should have a linear model for this. Let's see. How do I want to take a look at this? Well, let's go ahead and print. So my housing model dot coefficient. So it's coefficient with an underscore there. If I run that code, these are my two coefficient models. So essentially what we're doing, and I'll kind of explain this as well, right? Typically a line has that form y equals mx plus b. Well, we've picked two variables. So essentially it's going to be y equals m1x plus m2x for our two variables in x, and then plus b. So there will also be an intercept as well. So print housing model dot intercept. Linear regression has no thing interest. Again, we need that underscore at the end. That's the syntax. So basically what this is saying is that my model is going to be y equals negative 0.64 x1 plus positive 4.5 x2. Those are my two slopes, plus 2.54 as my intercept. So again, we have this linear model out there. And so we created our model. Now let's evaluate our model. We actually know what the line looks like, so let's evaluate the model. This is where we want to bring in that testing data that we set aside. We're going to take that testing data we set aside, and then we're going to actually plug it into our model and see how well it works. And so the way it created our model is it used the least squares regression algorithm to create that model, which is where it took all of our training data and it minimized the distance from the predicted value to the actual value. And that's how it created the model. So we're going to plug in the data we set aside, that testing data, and see how far away those predictions are as well. And hopefully that's kind of minimized with our mean square error. So, okay, so we want to evaluate the model, so we need to figure out what it's going to predict. So we're going to create a new object called the price predictions. And that's going to come from our housing model dot. And now we use the predict function, and we want to predict it across our X testing data, right? We set aside that testing data. And so we're going to plug that testing data into like the X coordinate for our line, and then store it as our predicted price. And then we're going to compare that predicted price against the Y testing data that we set aside. So once we did that, now I'm going to go ahead and print. So this is the R squared. So again, R is our correlation coefficient. So R squared is that correlation coefficient squared. It makes it positive. It also makes, when we have very small values, it makes them even smaller. So the closer to 1, the better we are. The farther away from 1, it's going to get even worse. And typically, again, that's just kind of what we use. So R squared, we need, let's do a colon. And then, okay, so again, here's a part of the code. I'm just going to kind of tell you what it is. We need the percent symbol, then the dot for F, close the parentheses, and then space percent. I might be doing this slightly wrong. We'll see. Model.score, and then X underscore test, Y underscore test. We got to close everything. Let's see. Model. Oh yeah, it's the housing model. Housing underscore model. Whoops. Okay, good. All right. So I actually did do that right. Oh man. I know that syntax is a little weird. So our R squared value, that is our correlation coefficient. So the correlation coefficient we got from our housing model from the test data was 0.7. So that's pretty good. That's pretty good for a correlation coefficient based on our testing data. Let's keep going though. Let's visualize the error here as well. So plt dot scatter the Y test. So I want my testing data along my horizontal, and I want to compare that to the price that I predicted, that object that I created in that last line of code. So I guess I'm a little out of order here, but that's okay. So again, I just want to visualize that as my X and my Y. Again, if you want to include the X equals, Y equals, you can. By default, you don't really have to. But I suppose it's probably good code to do that. And I do want my label, so plt.xlabel is going to be the, maybe I will be more specific here, right? Because y test and predicted price. So again, my x is the actual price. Let's do this a little bit nicer. plt.ylabel. That is going to be my predicted price. And so I want to do the plt.show. So let's think about what this would look like if it worked really, really well. If the actual price and the predicted price are always the same value, then we would expect they would have a one-to-one correspondence, and hopefully we would have a perfectly a perfect line with a slope of exactly 1. So let's see. All right, so that's actually not too bad. It definitely seems weird. My predicted price seems to be capped at 35, where the actual prices, again, we have this whole group that was a little bit higher. It feels like this part should be up here. Again, we kind of noticed that it seemed to be capped at 50. So I wonder if that kind of restricted my model a little bit. Again, if I was doing this and I was, going to be presenting this to my boss, I'd probably go back and look at those 50s. But let's try to finish this up. And actually, this is probably pretty good. Actually, I think this is probably a pretty good place to stop. We could definitely get one more piece of data to try to analyze how well my model did. So again, we evaluated my model. We found that R squared value, what the correlation coefficient was, and we visualized the error. The last thing we want to do is we want to actually find the mean squared error. That is our, or the MSE. That is our evaluation for linear regression. That is how we tell how well our model actually did. And that's kind of like that feedback loop. So we'll need to pull from sklearn one last time, sklearn.metrics. So again, that's a part of the package that actually lets us kind of evaluate how well we did using our different evaluation methods for machine learning. And I want to, from there, I just want to import the mean squared error function. And so from there, my MSE, again, I'm going to create a new object, and that is just going to be, again, I'm going to apply my mean squared error function to the y test. Again, the actual price, right? The y test is my actual price. Compared against my predicted price, or the price that my model predicted. So I'm creating that object. Oh, yeah. I better print my mean squared error as well. So I'll run my code. No module named sklearn metric. Oh, it's got to be metrics because there's multiple ways to evaluate. Let's do that. So my mean squared error is 27. And again, that's something that we would include. Hey, how well did your model do? Well, my mean squared error was 27. The R squared, here's the graph. And those are all ways that we can go ahead and see how well our model actually did. All right, so that was a lot. And I know a little bit of hand waving maybe. I tried to explain as best I could. I know we're still learning Python here. So if you have any questions, please feel free to email me. Or contact me in some way, and hopefully this was useful. Hopefully you were able to follow along and code this project on your own. All right, and as always, take care of yourselves.